If you dropped a marble on a smooth table and tilted it slightly, you'd expect it to roll in a straight line. That feels obvious. That feels efficient. So here's a strange thing. Water almost never does that. Give water a slope, gravity, and plenty of time, and instead of drawing a straight line across the land, it starts to wander. It loops, it doubles back, it scribbles, and that raises a really good question. If water always takes the easiest path, why do rivers so often take the long way around? Let's talk about why. If you've ever looked at a map, maybe a road atlas, or just zoomed way out on Google Earth, you've probably noticed something interesting. Nature is kind of a messy artist. Roads go straight, property lines go straight, canals go straight, but rivers almost never do. They twist and loop and wander across the land like someone checking to see if their pen still works. And once you notice it, you really can't unsee it. No matter the continent, no matter the climate, rivers seem to prefer curves. In fact, finding a naturally straight river is actually pretty rare. When we do see long, straight channels, they're almost always engineered. Humans dredge them, reinforce the banks, and force the water to behave. Straight rivers are usually a sign of human control. Left alone, a river almost always starts to wander, which is funny, because water is supposed to be practical. Water tends to follow the path of least resistance. That's one of the first ideas we learn in physics. So here's the puzzle. If the shortest path downhill is a straight line, why do rivers take the long, winding way around? The answer isn't that rivers are inefficient. It's that they're solving a much more complicated problem than just getting downhill as fast as possible. To understand that, we need to look at how water actually moves. Even in a straight channel, water doesn't flow as one neat, uniform sheet. Friction slows the water touching the riverbed and the banks. The fastest flow ends up somewhere away from the edges, usually a little off center. So right from the start, rivers have fast lanes and slow lanes. And that unevenness matters. Now add momentum. Flowing water has mass, and mass in motion likes to keep moving the way it already is. So when a river gets even the tiniest nudge, a softer patch of soil, a fallen tree, a rock that refuses to budge, the fastest water doesn't instantly adjust. It pushes forward. And when that push happens in a bend, the strongest flow gets thrown toward the outside of the curve. That's where erosion really kicks in. Faster water carries more energy, and that energy can pry loose soil, sand, even chunks of land. Over time, the outside of the bend gets carved into a steep edge called a cut bank. If you've ever seen a river eating away at a grassy edge, collapsing it bit by bit, that's not random destruction. That's physics at work, focused in one place. Meanwhile, the inside of the bend is having a much calmer experience. The water there has a shorter path to travel, so it slows down. And slow water can't carry as much sediment. It drops what it's holding, sand, gravel, silt, building a gentle slope called a point bar. So every curve has a split personality. One side erodes, the other side builds, and the river slowly reshapes itself. There's also a hidden motion happening beneath the surface. In a bend, the flow often spirals like a slow corkscrew. Water near the surface moves outward, then dips down and sweeps along the bottom toward the inside of the bend. This spiral motion helps move sediment exactly where it needs to go. It's subtle. You usually can't see it unless you know what to look for, but it's one of the reasons river bends are so stable. So how does the first curve even start? It doesn't take much. Real landscapes are messy. Roots, rocks, uneven soil, old flood scars, animal burrows. One tiny imperfection is enough to deflect the flow just slightly. Once a bend exists, the physics takes over. The river doesn't plan the curve, it amplifies it. This is a classic positive feedback loop. A small curve sends fast water into the outer bank. That erosion sharpens the curve. A sharper curve focuses even more energy into that same spot. More energy causes more erosion. Round and round it goes. The river isn't choosing to curve. Curving is simply what happens when flowing water and loose sediment interact over time. Because of this, rivers don't just move downhill, they move sideways. Over decades and centuries, a river can migrate across its floodplain, slowly repainting the landscape. If you look closely at satellite images, You can sometimes spot faint crescent shapes, ghosts of where the river used to be. Those shapes are reminders that the river has been here before, in a slightly different place. Eventually, many rivers settle into large, smooth, repeating loops called meanders. At this stage, the river has found a kind of rhythm. It spreads its energy out instead of concentrating in one destructive line. These curves aren't random scribbles. They're a stable pattern for that particular slope, water supply, and sediment load. Change any of those, and the pattern changes too. But curves can grow too dramatic. When a loop becomes very tight, the river creates a narrow neck of land. During a flood, when the river has extra energy, it may punch straight through that neck. Suddenly, the river has taken a shortcut. The channel straightens. The flow speeds up. But even then, the story isn't over. The abandoned loop becomes an oxbow lake, a quiet crescent of water sitting beside the new channel. Over time, it fills with sediment and plants, turning into marsh and then meadow. It's like the river's old handwriting slowly fading from the page. The landscape remembers, even when the water moves on. So why do rivers curve across the land? Because a curved channel is often the most efficient way for a river to manage its energy. Curves let a river erode where it's strong, deposit where it's weak, and constantly adjust toward balance. A river is never finished, but it's always working toward a shape that lets it flow.